Welcome to the Quantanix YouTube channel. This is the Next Layer Podcast, episode 12. And today, oh boy, we are taking a deep dive into something huge: neural networks and deep learning. These things are, well, they're fundamentally reshaping how machines learn, how they see, even how they understand language.
They really are. And we've gathered quite a bit for this one. Got a stack of sources here, articles, research papers, notes, really focusing in on the technical side, the nuts and bolts.
Exactly. So our mission today is not just definitions. We want to unpack the core principles, lift the hood a bit on the architecture.
And understand how they actually learn, which is pretty ingenious when you get down to it.
Right, and show you where this power is making a real difference. We're aiming for clarity, insight, but hopefully without, totally burying you in jargon.
Think of it as getting the core concepts that drive so much of modern AI, the foundational ideas.
Okay, let's dive in then. Unpack this. Where did this whole idea even start? Were people actually trying to build like an artificial brain?
Well, the inspiration, yes, definitely rooted in the biological brain. The early pioneers were absolutely looking at how neurons work, how they process information, pass signals, adjust connections based on experience. That was the conceptual starting point.
And that led to the first models, the early attempts.
Precisely. And one that always comes up, really foundational, is the perceptron, Frank Rosenblatt, back in 1957. And our sources, they really stress this wasn't just, a historical footnote. It was the first real demo that a simple artificial unit could learn a task, like classification. It showed potential.
Okay, so what is this perceptron then? How does it actually work?
It's basically the simplest artificial neuron you can imagine, a supervised learning algorithm designed for binary classification. Two categories. You feed it inputs. Each input gets a weight, like a score of importance. Sum those up, add a bias term.
Like a little adjustment knob?
Kind of, yeah. Then pass that sum through an activation function. Basically a decider. Does it fire or not? Which category does it fall into? And it learns by tweaking those weights over and over.
Got it. So it learns the right scoring to sort things into two piles.
Yeah.
But, okay, here's where it gets tricky, right? And the research highlights this clearly.
Yeah.
The perceptron had a big limitation.
Oh, absolutely. It could only solve problems that were linearly separable. Meaning you could draw a single straight line or like a flat plane in more dimensions to perfectly separate the two groups of data points.
So for anything more complex, I remember the classic XOR example, which you can't separate with one line.
Yeah.
The perceptron just failed.
Exactly. It couldn't handle it. And that limitation, well, it was a major factor in the first sort of AI winter. People realized, okay, real world stuff, almost never neatly separable like that.
And we needed something more.
We needed multiple layers. We needed nonlinearity. That single layer limitation directly pushed development towards deeper, more complex networks.
Right, makes sense. You can't build a complex machine with just one type of simple gear.
Right.
And underneath all this, making it learn. That's a ton of math involved, isn't it?
Yeah. Oh, yeah. But it's actually quite elegant conceptually. The sources frame the whole training process as basically a big optimization problem. The goal is to find the absolute best set of settings for all those internal parameters, the weights and biases, the ones that make the network make the fewest mistakes on the data it's seen.
So it's not random guessing. It's systematically searching for the best configuration, like tuning an incredibly complex instrument.
Exactly like tuning. We use something called a cost function or loss function to measure how wrong the network is, how big the error is. Then the training uses optimization algorithms drawing heavily from calculus, linear algebra to tweak those weights and biases bit by bit to make that error, that loss, go down.
Like rolling downhill in that error landscape you mentioned.
That's a perfect analogy. Trying to find the lowest point, the minimum error, just by feeling the slope around you. That slope is the gradient.
Okay, let's break down the parts of that landscape. You mentioned layers. Is that just stacking perceptrons on top of each other?
Conceptually, yes. But organizing them into layers gives it structure, power. So you have your input layer that just takes in the raw data. Then you have one or more hidden layers. This is where the real computation happens. The network learns features, abstract representations of the data.
So it's not just passing data along, it's transforming it.
Exactly, transforming it. And finally, an output layer gives you the result, the prediction or classification.
And the deep in deep learning comes from having lots of those hidden layers.
Precisely. The depth is key. More layers allow the network to learn a hierarchy of features. Simple stuff in early layers, like edges in an image.
Combined into shapes in the middle layers.
And then recognizing whole objects or complex concepts in later layers, that ability to learn hierarchical representations, that's what makes deep networks so powerful. The sources really emphasize that depth.
Okay, but wait. If the basic neuron just does a weighted sum and the perceptron was linear, wouldn't just stacking them still be linear? Where does the ability to handle nonlinear stuff come from? What's the secret sauce?
Ah, yes. The crucial ingredient, activation functions. They are absolutely essential. After a neuron calculates its weighted sum, the activation function applies a nonlinear transformation to it. Without that nonlinearity, you're right, the whole stack would just collapse mathematically into a single linear layer. You wouldn't gain any power.
So the activation function lets it bend the rules, model curves, and complex shapes in the data.
Exactly. It decides if the neuron fires and how strongly, introducing that necessary nonlinearity. The sources track the evolution here too. Early ones like sigmoid or ton worked.
But they had problems, right? Especially in deep networks.
They did. The infamous vanishing gradient problem, the signal telling the network how to adjust weights, got weaker and weaker as it went back through many layers, especially with those functions.
So learning stalled out in the early layers.
Pretty much, and that's where ReLU, the rectified linear unit, came in and really changed the game.
That's a simple one. Max, 0, input.
Yeah.
Just passes positive values, zeros out negative ones.
Yeah. That's the one. And the research highlights a key insight. Its simplicity makes it super fast computationally, but more importantly, it helps massively with that vanishing gradient problem compared to sigmoid or tan.
Allowing much deeper networks to actually train effectively.
Right. Then you get variations like leaky ReLU to handle cases where neurons could just die off if they always got negative input. And for the output layer, especially for classifying into multiple categories, you often use softmax.
Which turns the final scores into nice probabilities that add up to 1.
Exactly. So the choice of activation function, it really matters for performance and training stability.
Okay, functions add nonlinearity. What about the weights and biases themselves? You call them learnable parameters.
Yep. They are the knobs the network tunes during learning. Weights control the strength of the connection between neurons. How much influence does one neuron's output have on the next? And biases. They're like an offset. They let a neuron shift its activation threshold, making it easier to fit the data patterns. It gives the neuron more flexibility.
And these are the things that change during training. They start random.
They usually start with small, random values, yeah. Then, through the whole learning process, they get adjusted iteratively. The final values they settle on, that is the learned knowledge. That's the pattern the network found in the data. That's its memory.
Okay, let's talk about that learning process. How does it actually do the tuning? You mentioned forward propagation first.
Right. That's the first pass. Input data comes in, flows through the network layer by layer. Neurons calculate their weighted sums, apply their activation functions.
Outputs become inputs for the next layer.
Exactly. It's a cascade transforming the raw input into that final output prediction.
The network's best guess, based on its current weight.
Its current state, yes. And then, crucially, you compare that guess to the actual right answer. Calculate the error using that loss function.
Okay, now the clever part. How does it use that error to fix itself?
Backpropagation. This algorithm, honestly, it's the engine that made deep learning practical.
The cornerstone, you said.
Absolutely. Before backprop was well understood and efficiently implemented, training deep networks was, well, let's just say extremely challenging. What backprop does is provide a really efficient way to compute the gradient of that loss function. Remember the slope analogy. It tells us how much each single weight and bias in the entire network contributed to the final error.
And which way to adjust them to reduce the error.
Precisely. Which direction and how much. It's called backpropagation because you start with the error at the output and propagate that error signal backwards through the network.
Layer by layer, assigning blame.
That's a good way to put it, assigning responsibility for the error. And it does this calculation incredibly efficiently using the chain rule from calculus.
Calculus comes back to haunt us.
Hey, it's unavoidable here. But the beauty is, backprop gets you all the gradients you need for every parameter in just one pass backwards.
And those gradients tell the optimizer what to do.
Exactly. They feed into the optimization algorithm, which is usually some form of gradient descent.
Right, the downhill analogy again.
Yep. Gradient descent uses those gradients to iteratively update the weights and biases, step by step, moving in the direction that reduces the error the most steeply.
Trying to find that valley floor, the minimum loss.
That's the goal. You have the cost function as your landscape, the parameters define your position, the gradient points downhill.
And key things here are the learning rate.
Right. How big are the steps you take? Too big, you might leap over the minimum. Too small, training takes forever.
And how you initialize the weights at the start. Where you begin on the landscape matters.
It does. And this whole process repeats. Feed data, calculate error, backpropagate, update weights, over and over through batches of data, thousands or millions of times, until the network's performance is good enough.
Wow. Okay, so that's the core machinery. But you mentioned different types of networks. It's not all just these basic feed-forward layers stacked up.
Definitely not. While those feed-forward neural networks, or FNNs, where information just flows straight through, input to output, no loops are the foundation.
The vanilla version.
Sort of, yeah. They're great as general function approximators, good for tabular data, things where input A maps directly to output B, depth gives them power. But they have limitations.
Like what?
They don't have any built-in understanding of, say, spatial structure in an image or time dependencies in a sequence. They treat all inputs independently.
Which is a problem for pictures or language, right? This is where things get specialized.
Exactly. For images, you have convolutional neural networks, CNNs. These were a revolution for computer vision.
How do they work differently?
They're designed for grid-like data. The key is the convolutional layer. Instead of connecting every neuron to every neuron in the next layer, it uses small filters. Think tiny feature detectors that slide across the image. One filter might learn to detect horizontal edges, another diagonal lines, another a specific texture. And crucially, it uses the same filter across the whole image.
So it can find that edge anywhere.
Yes. That's called translation invariance. And because the filter is shared, it dramatically cuts down the number of parameters the network needs to learn. Much more efficient for images.
Clever. And they stack these layers too.
Yep, often alternating convolutional layers with pooling layers, which basically shrink the image size, making the network more robust to small variations. Then usually some fully connected layers at the end for the final classification. CNNs learn this amazing hierarchy of visual features.
Okay, CNNs for seeing. What about hearing or reading? Things that happen over time, sequences where order is critical.
Right, that's where FNNs and CNNs fall short. For sequential data, text, speech, time series, you need recurrent neural networks. RNNs.
Recurrent, meaning they have loops.
Exactly. They have connections that loop back on themselves. This allows information from previous steps in the sequence to persist and influence the processing of the current step. They have a kind of memory.
So they can remember what word came before the current one.
Essentially, yes. They maintain an internal state or context that makes them naturally suited for language modeling, translation, speech recognition.
I feel a but coming.
Hey, yeah. Standard RNNs, while good in theory, struggle with long sequences. That vanishing gradient problem pops up again. The memory fades too quickly. Information from many steps ago gets lost.
So they have short-term memory issues?
You could say that, which led to more complex RNN variants, LSTMs, long short-term memory networks, and GRUs, gated recurrent units.
Gates, like controlling the flow of information.
Precisely. They have these internal gating mechanisms, learned switches, really, that carefully control what information gets stored in the memory, what gets forgotten, and what influences the output. It lets them maintain context over much longer periods. These were huge breakthroughs for NLP.
Wow. Are there other big architectural advancements?
Well, one more the sources mention is ResNet residual networks. This tackled a different problem. People found that just making standard networks deeper and deeper didn't always help. Sometimes performance got worse after a certain depth.
Counterintuitive. More layers hurt.
Yeah, the degradation problem. ResNet introduced skip connections or residual connections.
The signal jumps over layers.
Kind of. It allows the input from an earlier layer to be added directly to the output of a later layer, bypassing some layers in between. It turns out it's often easier for a layer to learn the difference, the residual it needs to add, rather than learning the entire transformation from scratch. This simple idea fundamentally helped with gradient flow and allowed training of incredibly deep networks, hundreds, even over 1,000 layers, pushing performance boundaries again.
Incredible ingenuity. So, bringing it all together, where is this tech actually changing things now? What does this mean for us, for you listening?
Oh, the impact is everywhere. It's not hype. In computer vision, self-driving cars identifying obstacles, medical scans being analyzed for disease detection, often better than human experts, facial recognition.
Yeah, my phone unlocks with my face. That's probably a CNN.
Very likely, yes. Then NLP, think virtual assistants like Siri or Alexa understanding you, Google Translate getting eerily good, chatbots, even AI generating articles or code.
So much of the smart tech we interact with daily.
Absolutely. Healthcare is huge. Disease diagnosis, drug discovery, predicting patient outcomes from records, finance spotting complex fraud patterns, algorithmic trading, assessing risk, manufacturing checking product quality on assembly lines, predicting when machines need maintenance.
It really seems to be anywhere there's complex data and subtle patterns to find.
That's the key. Their power lies in learning those intricate, often non-obvious patterns directly from data, often at scales humans just can't handle.
So what's the next frontier? Where are things heading based on the research?
Several trends stand out. Transfer learning is massive. Reusing large pre-trained models as a starting point for new tasks saves incredible amounts of time and data.
Like giving the network a head start.
Exactly. Also, few-shot or zero-shot learning, trying to get networks to learn effectively from very few examples, or even just a description more like humans do. Attention mechanisms and the transformer architecture, which came out of NLP but are now used everywhere, allow models to dynamically focus on the most relevant parts of the input. Very powerful.
And you mentioned privacy.
Right. Federated learning is growing. Training models across many devices without the raw data ever leaving the device. So you get the benefit of diverse data while preserving privacy.
This has been, well, quite the journey. From that simple perceptron inspired by the brain through backprop, all these different architectures, to the world-changing applications we see now.
It really highlights this convergence, doesn't it? Clever algorithms, massive data, powerful computers, all built on that core idea of mathematical optimization finding patterns.
It's the bedrock of so much modern AI.
Undeniably. And it's not standing still. The sources all point towards continued rapid progress, better algorithms, more compute, more data. It's a cycle driving incredible change.
Which leaves us with a thought, maybe a challenge for you listening.
Yeah, building on what the sources suggest about the future, these technologies are going to keep evolving, keep getting better at seeing, understanding, generating. So the question is, how might this ongoing evolution, this relentless progress in neural networks and deep learning, how might it change your specific world, your job, your industry, your daily life? Maybe sooner than you think.
Definitely something to ponder.
Mm-hmm.
Thank you for joining us for this deep dive into neural networks and deep learning. Like, subscribe, and stay tuned for more deep dives in the Next Layer podcast at the Quantanix YouTube channel. Thanks for listening, and give that question some thought.